Hello everyone, welcome to our walkSTEM tour of Central Park. I will be guiding you on this tour today. We have 4 iconic stops on our tour: the slide at the 72nd Street Playground, the Bethesda Fountain, the Central Park Carousel, and the swing in the Heckscher Playground. Let's get started. Now we are at the slide. Notice that there are kids of all ages sliding down. Why is it easier for a child to go down a slide as opposed to an adult? Will the adult create more friction? Before you guess, let me remind you that kinetic friction is calculated using the normal force and coefficient of kinetic friction. As you can see in diagram 1, kinetic friction is equal to mu k times the normal force. And in diagram 2, the normal force is the force perpendicular to the surface that an object is resting on. The magnitude of the normal force is dependent on the component of weight force. Do you think you can answer the question now? The answer is that an adult will have a larger normal force and therefore have a greater force of kinetic friction. The adult will create more friction going down the slide. However, so that everyone goes down the slide quickly, the surface of the slide is created so that the coefficient of kinetic friction is minimized. Welcome to the Bethesda Fountain, a classic tourist location in New York City. Take a look at your reflection in the water of the fountain. Have you ever wondered why your reflection is distorted in water? This is due to different types of reflection, depending on the smoothness of the surface. There are 2 main types of reflection: specular reflection and diffuse reflection. Based on diagram 1, which type of reflection do you think is seen when you look into the water in the fountain? Your reflection in the fountain is an example of diffuse reflection, because due to the water droplets that create ripples in the water, light hits the water and reflects in many different directions. This is why your reflection looks distorted. In diagram 2, the water is completely still and you can see a nearly perfect looking reflection on the water. This is specular reflection, and it is only seen when the surface is completely flat so that all the light is reflected evenly at a definite angle. We are now at the Central Park Carousel. Notice that there is an outer and inner ring of horses positioned on the carousel. Do you think that the outer and inner horses are moving at the same angular velocity? They may seem like they are, but the angular velocity is really defined as the angular displacement of an object during a time interval as seen in diagram 1. With this information, do you still think that the horses are traveling at the same velocity? The horses on the outer layer of the carousel are actually moving at a higher velocity because they are traveling a greater distance than the inner horses during the same time interval. You can see in diagram 2 that the horses farther from the center of the carousel will have to travel a greater distance over time. Welcome to the Heckscher Playground. How do you think the length of the chains on the swing affect how fast you can swing? When you swing back and forth on a swing, your motion models that of a pendulum, shown in diagram 1. This physics concept demonstrated is simple harmonic motion. If you pull the swing back at a small angle, the time it takes the swing to move back and forth is the same time it takes if the angle is very large. The time it takes the swing to move back and forth is called the period, and the equation is shown in diagram 2. This equation means that the period equals 2 pi times the square root of the length of the chain divided by the acceleration due to gravity. Therefore, the only thing that affects the period and frequency of the swing is the length of the chains when the applied force is held constant. The longer the length of the chains on the swing, the lower the frequency, which means that the swing will move back and forth less times in a given time period than a swing with shorter chains. Therefore, if you have 2 swings, one with longer chains and one with shorter chains, and you pull them back at the same angle, the swing with the shorter chains will be moving faster. Thank you so much for coming with us on the walkSTEM tour of Central Park. I am so glad that I could be your guide on this incredible journey through the park, learning about these fascinating physics concepts. Come back next time, and thanks for walking.